Today, I'm very happy to introduce Dr. Isla Simpson. Dr. Simpson grew up in Scotland and got her education, undergraduate at the University of St. Andrews in physics and astrophysics. And after that, she moved to University College London and got her PhD in physics also. And the dissertation actually won the best dissertation prize in the physics department at University College. After that, she moved to Toronto, University of Toronto as a postdoc, and then finally went to Lamar in 2012. So she has a large number of quite exciting publications, including large-scale dynamics and regional, and recently in sort of regional climate in the Mediterranean region. So let's hear her talk. Thank you.
Thank you for having me here today. So I'm going to talk about this recent work. It's looking at the importance of topography for the large-scale dynamics and climate in the Mediterranean region. And so this has been done with Richard Seeger, Tiffany Shaw, and Ming Fan Teng, who are all at Le Mans. And so it's pretty recent work. We just submitted it to Journal of Climate last week, so I'll be very glad to hear if there are any comments on it. So the dictionary definition of a Mediterranean climate zone is one that's characterized by having mild, wet, variable winters when it's under the prevailing westerly winds, and then having hot, dry, calm summers. So there are various different Mediterranean climate zones of the world. So we've got California, there's a little bit of Chile here, a bit of South Africa, bits of Australia, and then of course the Mediterranean itself, which is the region after which all these different Mediterranean climate zones get their name. So during the winter, what these regions are characterized by, well, they're in the subtropics, so they're pretty mild. But they're under the influence of the prevailing westerlies and then mid-latitude storm systems that come along with that. And so what that means for them in the winter is that they're quite mild, but they're also kind of wet and variable. But then during the summertime, you have a pretty different situation set up. So during the summer, you get the subtropical anticyclones are set up in the ocean basins. So this is schematically depicting, it would be the lower tropospheric stream function. You get these anticyclonic circulations in the ocean basin during the summer, and then on the eastern flanks of these anticyclones, you tend to have subsiding motion. So that would be into the page. And so the Mediterranean climate zones in the world tend to lie under these subsiding eastern flanks of the subtropical anticyclones. And because you have subsiding motion, that gives you pretty hot, dry, and stable conditions over these regions during the summertime. Then the Mediterranean itself is kind of unique, I think, a little bit among the other Mediterranean climate zones of the world for a couple of different reasons. So during the winter time, most importantly, well, the Mediterranean itself has its own storm track. So you can see that in this paper by Bengtson et al., which is looking at storm track statistics. So this is a cyclone tracking density, and then this is cyclogenesis density. And so you see the storms are actually growing within the Mediterranean basin itself during the winter time, which is a bit different from the other Mediterranean regions. But then also I think perhaps more relevant for what I'm going to be talking about today is that the Mediterranean is kind of remote from the subtropical anticyclone for the most part in the Atlantic basin. So the top panel here, this is lower tropospheric eddy stream function during the summertime. So you've got anticyclonic circulations in both ocean basins. And then the lower panel is mid-tropospheric vertical velocity. So red is downward motion. So you see this subsiding motion on the eastern side of the subtropical anticyclone. So California and then the western part of the Mediterranean lie under this subsiding motion during the summertime. But then the central and the eastern Mediterranean, they've got really strong subsidence too there in this kind of bullseye in the central to eastern Mediterranean, but it's kind of remote from the subtropical anticyclone. So the dynamics, I think, are a little bit different, and that was really understood, I think, by Rodwell and Hoskins in 1996, where they talked about the importance of the Asian monsoon for the climate of the Mediterranean and the Sahara. And so they identified that, so during the summertime, you've got all this ascending motion and latent heat release over Asia here, and they recognize that that's important for producing this subsidence that you see in the central to eastern Mediterranean. So I'm going to go and talk a bit more about what Rodwell and Hoskins actually did, because what I'm doing is very highly motivated by their study. First of all, if it works, yes, it's working. So it's going to show this movie. This is of the seasonal cycle of vertical velocity. So what you have during the summertime is these localized regions of vertical velocity of descent in the eastern parts of the ocean basin, and then here over the Mediterranean. But then during the winter time, you have much more zonally symmetric subsidence. So this is really the descending part of the Hadley cell. That happens during the winter time, and then during the summertime, things become much more localized and organized into these particular regional features. So it's really going to be this bullseye of descent that I'm going to be focusing on. And so Rodwell and Hoskins identified how important during the summertime the Asian monsoon is for producing that. So the question that they were really addressing is why do you have this subsidence in the central to eastern Mediterranean and over the Sahara during the summertime? And I think the reason why this was confusing is I think historically it had kind of been assumed that it was just part of the zonally symmetric Hadley cell circulation. But that doesn't really work out when you look at what the zonal mean vertical velocity looks like. So this is during the winter, and this is during the summer. So during the winter, you've got the ascending motion just into the southern hemisphere, and then descending motion in the northern hemisphere subtropics. Whereas in the summer, you kind of had the opposite. And actually, during the summertime, when you have all this strong descent over the Mediterranean and Sahara, in the zonal mean, there's really very little descending motion there. So something else had to explain it, and so they realized how important the Asian monsoon is for that. And so what they did was it was a very simplified general circulation model. It's just a kind of a dry dynamical core model, and they ran it in a pretty simplified setup. So what they did was they started off with like the zonal mean basic state. So I just shown as an example here is the upper tropospheric zonal wind. So they started off with the zonal mean winds and temperatures. They put in the topography, and they put in the diabatic heating. So these colored contours here are just showing the vertically integrated diabatic heating. So you can see all this heating over Asia associated with the Asian monsoon in the summertime. And then they watch the model evolve. So you start off from the zonal mean state, you put in these perturbations, and let it evolve over time. So they watched it over 16 days. After that, the model went a bit unstable with baroclinic instability. But the hope is that in that time, you can kind of see the realistic zonal asymmetries of the real world being produced in response to these different forcings. And you would end up with something that looks like what they're trying to explain. So they managed to reproduce the descending motion over the Mediterranean and the Middle East pretty well. So this is the topography input they put in, and then the heating input. And then this is what they got. This is, I think, at day 16 of their model integration. This is the vertical velocity in the mid-troposphere. So solid is downward and dashed is upward. And so importantly, they were able to reproduce this, this descending motion over the central to eastern Mediterranean and North Africa by just putting in the heating and the topography. And so then they could use this model to try and pull apart what's important in producing this. So they went on to do some further idealized experiments, and they just started off by putting in idealized Asian monsoon heating. So only heating over Asia, starting off from the zonal mean basic state, and then letting the model evolve. And this is the vertical velocity response that they found. So they found that over the region where they heated, you got ascending motion, and then you get this descending motion here to the west. So that Asian monsoon heating alone can give you descent over the Middle East and the Mediterranean. And so through this, they proposed what they call the monsoon desert mechanism. So basically, this is explaining a large amount of the descent over the Mediterranean during the summertime. You start off with heating over Asia, That gives you ascending motion, upper level divergence. And then the balanced response to that is a gill-type Rossby wave solution. It consists of an upper level anticyclone and a lower level cyclone, and in balance with that you have descending motion further to the east. That's right, to the west. Then there's an additional part to this, and they said that this whole structure here is warm, so it's warmer over Asia, and then this interacts with the mid-latitude westerlies. So the mid-latitude westerlies are coming along, and if they're adiabatic, they're going to flow along the isotropes. And so if you warm this region, what that does is it makes the isotropes slope down towards it. And so then they argue that as the westerlies come along, they're going to flow down these more slopey isotropes, and that would give you more descent than in the Mediterranean. So that's really the mechanism that they use to explain how you get some of this descent here over the Mediterranean and Sahara during the summertime. But obviously this is not the complete story, because this doesn't look like the real world. It doesn't have these localized regions of descent that we see in the real world. And so then they argue, well, there's a further localization of descent by the topography. And so they find if you just put in the monsoon heating and you put in the topography, you start to get this localized region of subsidence in the central to eastern Mediterranean. But again, this is not completely like the real world. It gets you about halfway there. So they argue, well, if you put in Asian monsoon heating and you have the topography, you can get about half of the subsidence that you see in the real world. And then they argued for a further diabatic enhancement of that to give this full response. So they said, well, if you've got descending dry air, that lowers the level of radiative emission to space, and that would give you further diabatic cooling and then further subsidence. So to summarize this mechanism for how you end up with the subsidence in the central to eastern Mediterranean during summertime, you start off with the Asian monsoon heating. That gives you a Rossby wave structure, gives you some descent to the west. Then there's an interaction with the mid-latitude westerlies, that gives you more descent. There's a further localization by the topography, and then there's also this further diabatic enhancement. So the thing I'm really going to be focusing on here is this localization of the descent by the topography, and kind of revisit a bit what the influence of topography is on the Mediterranean in the summertime. During the Mediterranean. We had a couple of motivations for doing this. So the first one, which is really why I got started on this work, is I wanted to try and understand the future. So in the future, the Mediterranean, it really undergoes much more pronounced circulation changes than a lot of other regions in the world. And so motivated by Rodwell and Hoskins, I was kind of interested in looking at what the role of topography was for the future. But I kind of got a bit distracted by the current climatology, so I only have some very preliminary results on the future, which I'll show at the end. But the reason why we got a bit distracted by the current climatology is that it turns out in a comprehensive GCM, we actually obtained pretty different results from Rodwell and Hoskins as to the role of the topography. So the topographic influence was a very small part of the Rodwell and Hoskins paper, and they didn't really go into great detail in it, but we come up with a bit of a different answer as to what's important there, and also what the dynamics are a little bit different, I think, from what they hypothesize. So this is the topography surrounding the Mediterranean region of the real world. And so there are a couple of different mountain ranges that I'm going to focus on. So we've got the Atlas Mountains here, and then the Zagros Mountains that are here in the Middle East. So the Atlas Mountains they're primarily in Morocco, kind of meridionally elongated, so from southwest to northeast, and the highest peaks are over 4 kilometers. They're pretty narrow mountain range. And then the Zagros Mountains, mostly they're in Iran, orientated from southeast to northwest. They're higher than than the Atlas Mountains. Highest peaks are about 4.5 kilometers. So these are really the two mountain ranges I'm going to focus on. So here's what Rodwell and Hoskins said about the role of topography. So they showed, well, if you put in monsoon heating and you put in topography, you can kind of get this structure of localized downwelling in the central to eastern Mediterranean. So then they took out different parts of the topography in their model, and they showed, well, if they take out the Zagros Mountains, so they're the ones in the Middle East, it didn't really have an effect on the subsidence there. Whereas they found if they took out the Atlas Mountains, that kind of one contour there, localized subsidence, has gone away. And so they argued that the Atlas Mountains were really important for localizing the subsidence here in the central to eastern Mediterranean. So their overall conclusions as to the role of the topography was that, well, this is what they said in their paper, is that the terrain west or upstream of each descent center is most important for determining the location of the descent. So this is our summertime vertical velocity. So we've got subsidence here on the eastern flank of the subtropical anticyclone in the Atlantic. And then we've got these two regions of subsidence here. So this one in the central to eastern Mediterranean that I'm going to be mostly focused on. And then this one here east of the Caspian Sea. And then this is the topography. So they said, well, assuming the incident flow is from the west, as it hits these mountain ranges, you get an anticyclonic circulation over the mountain range, which would then give you northerlies to the east. And so if you have northerlies, and if they're adiabatic, in this region, this is the isotropes averaged over the Mediterranean region as a function of latitude and pressure. So the isotropes are sloping, and so if you have northerlies and they're adiabatic, they also have to be going downward. And so you can then see why, if this circulation is produced, that would give you subsidence here, and then this would give you subsidence there. So it turns out that we get a bit of a different answer as to which mountain ranges are important. So, and it really turns out in a comprehensive GCM that the Zagros Mountains are actually, the ones to the east of the Mediterranean, are actually much more important for influencing the climate there. And actually the incident flow is not from the west on these mountain ranges during the summertime, it's actually from the east. And the dynamics of the mountain influence, I think, are a bit different than what Rodwell and Hoskins originally hypothesized. So the model experiments that I'm using are using CAM5 at 1.9 by 2.5 degree resolution with a finite volume dynamical core. All the simulations are 100 years long, so, and all the anomalies I'm going to show are very statistically robust. They were just done with prescribed sea surface temperatures and just time slice experiments with year 2000 greenhouse gases. So this is again the topography of the real world. And this is the topography of the CAM world. So obviously things become pretty smoothed out on the model grid. The mountains are shorter and smoother. But we still have the main mountain ranges that we're interested in. So we've got the Atlas Mountains here and the Zagros Mountains here. And even though the topography is pretty smooth in the model, it still does a reasonably good job of simulating the features that we're interested in over the Mediterranean. So I'll just demonstrate that now. So this is the year interim vertical velocity during the summertime, which is, I've already shown a number of times. So these features are going to be what we're interested in, is subsidence here, and then we've got ascending motion that's kind of seems to be co-located with the mountain ranges that I'm looking at. And then this is comparing the year interim climatology with the CAM5 model climatology. And so it's not 100% perfect, magnitudes are a little bit off, but it certainly is producing the main features that you see in the real world. You've got this localized subsidence here, and then this ascending motion over, located where the mountains are, and then this further descent to the east. So that's vertical velocity. It seems to look pretty good in the model. Shows some other fields. So these are all fields I'm going to show to look at the mountain influence. So this is lower tropospheric meridional wind. So red is southerly and blue is northerly. So in the real world, you've got this quite intense northerlies over central to eastern Mediterranean and North Africa. And these are separated from northerlies on either side by southerlies, which kind of coincide with the mountain ranges that we're looking at. And this is comparing now year interim with CAM5. And again, CAM5 seems to get these main features. Magnitudes are, these northerlies are a little bit weaker, but it's definitely capturing the main features that we're looking at. And then the final field I just want to show is upper tropospheric meridional winds. So this is 300 hectopascals in the real world, and you see that over the Mediterranean and further to the east, there's a lot of waviness in the upper troposphere across the whole region. And then this is again comparing the real world with CAM5. And CAM5 is really producing these main features that we see of the upper level waviness. So I think we can be confident enough that the model is reproducing the main features of the circulation. So we can use it to look at what's the influence of topography. So we've done 4 experiments. So the first one is just a regular control run with all the topography there. And then the other ones, we flattened topography in these boxes. So this first box here, that contains the Zagros Mountains. And then the second box here contains the Atlas Mountains. And then I also flattened this other range down here, the Hagars, if that's how you pronounce it. So we did one where I'll call that both flat, where we flattened both boxes. So we really removed all these mountain ranges that we're focusing on. And then another one I'll call Zag flat, which is where I only removed the topography in this box, so we removed the Zagros Mountains. And then the final one where I only removed the topography in this box, so primarily removing the Atlas Mountains. So we can use this to ask, well, what's the mountain influence on the circulation? So this is the full topography, vertical velocity with this localized region of subsidence. And then this is what you get when you remove those 2 mountain ranges. So it's pretty different. The mountains in this region are having really quite a big influence on the circulation. And they're actually, when you don't have the mountains, well, the mountains are responsible for about 30% of this bullseye of subsidence in the central to eastern Mediterranean. And when you remove the mountains here, you no longer have this ascending motion here. And you can also modify the descent to the east as well. So this, without the mountains, is presumably kind of the direct influence of the Asian monsoon. We haven't tested that, but that's what Rodwell and Hoskins said, is that you can have this ascending motion and latent heat release further to the east over Asia, and that will give you descent in this region. But then it's clearly highly modified by the topography. And so we can then show what's the influence of the topography by taking the difference between the full run and then the one with the mountains flattened. And this is what you get. And so the topography gives rise to this like ascent over where the mountain ranges are. So here's the Atlas Mountains and the Zagros Mountains. And then a bit of descent here, and then in the central to eastern Mediterranean, and then further to the east. And then we can use the other 2 experiments to ask, well, what's the influence of the different mountain ranges? So this is the influence of the Atlas Mountains. So Rodwell and Hoskins found that the Atlas Mountains were the most important in localizing the descent in the central to eastern Mediterranean. But it turns out here they're having a bit of an influence, but they're really not the most important. And you still mostly have the structure that you have in the full climatological subsidence with the full topography, even when you remove the Atlas Mountains. So what the Atlas Mountains are doing is they're giving you ascent over the Atlas Mountains, and then descent to the west, and a little bit further to the east. Whereas if you look at what the Zagros Mountains are doing, so these are the ones that Rodwell and Hoskins found didn't really do anything in their model. In the full GCM here, the Zagros Mountains are really having the most important influence on the subsidence in the central to eastern Mediterranean. And they're producing a tripole in vertical velocity, just like the Atlas Mountains are. You've got ascent over the Zagros Mountains, and then descent to the west and to the east. So overall, it's kind of a little bit fortuitous, I think, the separation of the Zagros and the Atlas Mountains. They're both kind of giving you the same structure of circulation. They're giving you ascent, a tripole with ascent, and then descent. And so the Zagros Mountains are doing that, and then the Atlas Mountains are kind of doing the same thing, but to a lesser extent. But they're kind of both conspiring to give you descent in the same region here, kind of over Greece and Libya. But it's really the Zagros Mountains here that seem to be the most important, which is quite unlike what Rodwell and Hoskins found in their model. So So we can look at other fields. So this is a lower tropospheric meridional wind again, and we have these strong northerlies in the full topography run over the central to eastern Mediterranean. And when you remove the topography, they become much weaker. So really the topography is really responsible for the presence of these northerlies here. So we can look at, again, take the difference between these two, and it tells you what the topography is doing. It's giving you northerlies here, and then southerlies over the Atlas Mountains and the Zagros Mountains. And we can look at the different mountain ranges individually again. So the Atlas Mountains is kind of weak, but there is a tripole, southerlies and then northerlies to either side. And then the Zagros Mountains are kind of doing the same thing, southerlies along their axis and northerlies to either side. So again, they're kind of separated by just the right amount and having a similar influence on the circulation, that they're both kind of conspiring to give you northerlies over the same region, over the central to eastern Mediterranean. So the Zagros Mountains are more important to the north, and the Atlas Mountains are more important to the south. And then the final field I want to show is just the upper tropospheric meridional wind again. So this is, again, in the full topography world, you have a lot of waviness over climatological stationary waves over this region in the upper troposphere. And this is what you get when you don't have those mountain ranges there. So they really have a very big influence on the upper level circulation. And so you can see what that influence is there. So in the full topography around here, you've got northerlies of about 4 meters per second. And when you don't have the topography, you've got southerlies of about 4 meters per second. So the topography is really completely altering the structure of the circulation in the upper troposphere. And I think further downstream as well to the east. And I haven't really looked in more detail further to the east, but I think there could be some interesting influence of the topography there as well. So yeah, again, we can just say what's the influence of the different mountain ranges. So this is the Atlas Mountains. It's kind of a little bit weaker than what the Zagros Mountains are doing. They're producing this big upper level wave train that kind of is advected towards the east along the west. There's strong westerlies there during the summertime. So both the Zagros and the Atlas Mountains are kind of conspiring to give you descent in that region in the central to eastern Mediterranean. They're responsible for about 30% of that descent during the summertime. And they're also largely responsible for the northerlies that happen over the central to eastern Mediterranean as well. But really, in contrast to the previous work that has looked at this, it really seems to be the Zagros Mountains that are the most important contributor to this. And I don't really know why our results would differ to theirs, but their model was a very idealized model, and it was run quite a while ago with a short amount of reanalysis data used as the input. And I think given that the model we've used is kind of reproduces the main features of the circulation, I think we can have quite a bit of confidence that this is true in the real world as well, that the Zagros Mountains are really important for the circulation in the Mediterranean during the summertime. So another question that we can address with this model, which Rodwell and Hoskins couldn't look at in their idealized setup, is what's the influence on the hydrological cycle in the Mediterranean. So this is looking at the climatology in the model. So precipitation, evaporation, and then precipitation minus evaporation, focused in now on the Mediterranean. So during the summer, there's very little precipitation over the Mediterranean. But there's a lot of evaporation, and so the Mediterranean is really at a moisture deficit during the summertime because of all this evaporation. And so now I'll show what's the influence of the Zagros Mountains on that. I'm going to focus on the Zagros Mountains from now on because they're really what are doing the main thing. And so this is the influence of the mountains by taking the difference between the one with the mountains and the one without. So they don't do a whole lot to precipitation, I think, because there isn't really much precipitation there anyway. But they do change the evaporation quite a bit. And so these contours here, they're about 25%, they are 25% of the contours that I showed for the climatology. So the Zagros Mountains act to enhance the evaporation over the Mediterranean quite a bit. And they're responsible for quite a good fraction of the negative P minus E that you have there during the summertime. So if we just compare directly with the climatology, so we're talking about approximately 20% of the moisture deficit during the summertime over the Mediterranean can be attributed to the presence of the Zagros Mountains and the circulation that they induce. So they're inducing this subsidence, the low-level divergence and moisture divergence away from the region, and then enhanced evaporation. And so if you take an average over the Mediterranean Sea and you calculate what's this in like a moisture flux, it's about 0.03 spur drops, which I'm not really used to dealing with spur drops, but to put that in perspective, it's equivalent to about the freshwater input of about 4 Nile rivers before it was modified for irrigation purposes. So it seems like quite a big influence. So about 20% of the summertime moisture deficit can be attributed to the Zagros Mountains. So obviously these mountains are having quite an important influence on the circulation in this area. So I think it's important to understand what are the dynamics behind this influence. So there are a few different possibilities. So the obvious one is that it could be a mechanical influence. So you could either have flow coming from the west or from the east, hits the mountain barrier, and that generates circulation anomalies, which is giving what we see. There are other possibilities too. So one is that the mountains could be acting through as an elevated heat source. So the land kind of emits energy to the atmosphere through sensible latent heat fluxes. And so what that means is, like on the top of the mountain here, you're going to warm the atmosphere, and that's going to be warmed more than the adjacent areas because they're further from the ground. And so through that effect, you could kind of have a thermally driven circulation produced by the mountains. And then there's another possibility which was proposed by Busun Huang for the case of the Himalayas, and that's that the mountains could alter the moisture transport and alter where latent heat releases are happening. So you could have moist air coming towards the mountains, and the mountains kind of determine where the precipitation and the latent heat fluxes are going to happen, and that could then influence the circulation as well. So we wanted to distinguish between these different effects. And so the easiest one we could test for is for the mechanical influence, first of all, because we can test for that using a stationary wave model. So this is a different kind of model. It's kind of similar to the Rodwell and Hoskins model, but it's run in a bit of a different way. The details are in Ting and Yu 1998, and if you're familiar with it, there's the Held et al. 2002 stationary wave review paper. That's the model. This is the model that was used in that paper. So basically, what you do is you impose a basic state, winds and temperatures, and then you look at the anomalous circulation that is produced by putting the mountain in it. So it's fully nonlinear, but it's only solving the equations for the anomalies in the presence of the basic state. It's not evolving the whole circulation. It's just evolving the anomalies. It uses sigma coordinates and rhomboidal truncation at wave number 30 and 14 vertical levels. But the important point is really that all it's doing is solving the vorticity, divergence, and thermodynamic equations. It doesn't have the representation of the physical processes like radiation or latent heat release or anything like that. So if we can reproduce the response in this model, then it's telling you that it's really the mechanical influence that's important because it doesn't have all these other aspects in it. So what you do with this model is you can take the 3D basic state from the run without the mountains. So this is what the lower tropospheric wind vectors look like. So 850 hectopascals. And then we go and plot the mountains in it and look at how the model responds. One thing I just want to point out though at the moment is that the incident flow that's incident on the mountains is actually from the east. So you can see the northeast flow hitting the mountains here. And so that's not what was assumed in Rodwell and Hoskins. So the same is true for the Atlas Mountains. During the summertime, you have easterly flow hitting these mountain ridges. So anyway, we can put in the full 3D basic state, put in the mountain, and then see what kind of circulation anomaly the mountain generates. So this is looking at the upper tropospheric meridional wind, where we had this Rossby wave train. So this is in the full model, and then this is what we get with the stationary wave model. So it's not perfect. the magnitudes are a little bit off. Now, you wouldn't expect it to be perfect because this model here is very idealized, and it's got idealized dampings in it that are not going to be the same as the dampings that you get in the full GCM. But really what you get is the same feature. You have pretty much the same structure, and the meridional wind responds to the mountains. So it produces that upper tropospheric wave train. And you can look at the lower tropospheric meridional wind. So in the full GCM, we had this tripole, southerlies along the mountain axis, and then northerlies to the west and to the east. And we can reproduce that again in the stationary wave model. Again, with the magnitudes are a little bit off, but really the same features are there. And then finally, we can look at the vertical velocity. So in the full GCM, we had this tripole, and then in the stationary wave model, we can also reproduce that tripole in vertical velocity. So I think the stationary wave model really tells us that the main aspects of the circulation response to the Zagros Mountains can really be understood via the mechanical forcing that the mountains are exerting. So we then want to understand, well, what's the dynamics behind that? So again, we've got easterly flow hitting mountains. This is just the zonal component of that. So it's definitely easterly. And it's easterly at all levels that intersect the mountains. So this is looking at a cross-section at 39 north. Dashed is negative, so easterly flow, and solid is positive westerly flow. This is the Zagros Mountains. This is surface pressure here. We're getting into the Himalayas and Tibet here. So all the flow that's hitting the Zagros Mountains at all levels is from the east. So what we really have to do is then understand how does the easterly flow produce the circulation that we see. So we're talking about, well, so the mountains are orientated from southeast to northwest, but if we just simplify things and we consider meridionally elongated mountains and easterly flow, this is looking down on the mountain, and then this is from the south. So the flow is transitioning quite quickly to westerlies above the mountains. So what would you expect from easterlies hitting the mountains? Well, you'd think that they would go up and over the mountain, but obviously then this produces vortex stretching and compression, and it's going to generate vorticity anomalies as well. So if we just work through what you'd expect from a vorticity perspective of flow coming towards the mountains. So this is the vorticity equations. So this is the Lagrangian derivative of absolute vorticity following a fluid parcel coming towards the mountains. So this is the relative vorticity. This is the planetary vorticity. And changes in the vorticity are going to be induced by vortex stretching, which is the term on the right-hand side. That's the derivative of vertical velocity with height. So if we think about easterlies hitting the mountains, they're going to go up and over the mountains. And it turns out that the vertical velocity is maximum at the lower levels. So you then have like vortex compression on the upslope. This is negative, and that should be giving you, inducing negative vorticity, or anticyclonic vorticity. So the flow will bend towards the right. And that will then end up giving you southerlies across the mountain, across the axis of the mountain, which is what we see. And this would also happen if you think about the thermodynamic arguments. So if we think about, we're in this region again where the isotropes are sloping, and so if the flow wants to go up and over the mountain, if it's going up and it's adiabatic, then it has to also be going north. So it makes sense that the flow should bend to the north on the upslope. On the eastern side of the mountain range. Then as the flow heads north, F is going to increase, so the vorticity would decrease even more, and some of the flow might turn back on itself and end up with this kind of anticyclonic circulation on the upslope. And then you have the opposite happening. Some of the flow will make it over the mountain, and you have descent on the other side. And the descent is maximum at the lower levels, so you have vortex stretching on the other side. Positive d omega by dp, and that will induce positive vorticity. The flow will then bend towards the left. And again, as F changes, the vorticity will change more. And you can end up, you see how you can end up with this kind of structure surrounding the mountains at the low levels. So I just want to show that that's actually what these fields do. So this is the d omega by dp. You've got vortex compression on the upslope, stretching on the downslope, and then anticyclonic vorticity on the upslope, and cyclonic vorticity on the downslope. So you can see where this tripole structure in meridional wind will come from. And then the question is, well, how does that perturb the upper levels? So easterly flow is hitting the mountains, but easterlies are not. You can't have vertical propagation of Rossby waves in easterlies. But the easterlies are pretty shallow, so this is, again, it's a zonal cross-section along 39 north. And so just above the mountain range, the flow is transitioning to westerlies. And this is the G potential height anomalies in response to the mountains. And so you see the kind of westward phase tilt with height, that the high is tilting west and the low on the west side is tilting west. And so this is indicating vertical propagation of Rossby waves. And I think, so the generation of these anomalies at the low levels is kind of enough to perturb the upper levels and produce a vertically propagating Rossby wave that is then advected towards the east by the westerly flow that's there at upper levels. So I think one more thing is kind of useful to look at is the thermodynamic budget of the circulation. So if we consider the flow to be adiabatic, which for the most part it is, the three terms that we're concerned with are the zonal advection of temperature, meridional advection, and then vertical advection, or the adiabatic warming and cooling. The delta here will be the response to the mountains, so the difference between the full run and the run without the mountains. So this is what these terms look like in the lower troposphere. So they approximately balance, and the only two terms that really matter are the meridional advection and the vertical advection. So what you really have is like the warm advection by southerlies is being balanced by the adiabatic cooling, and then the cold advection by northerlies is being balanced by adiabatic warming. So it's really adiabatic flow along the sloping isotropes. And so the descent that we see in the central to eastern Mediterranean is there throughout the depth of the troposphere. And so in the lower troposphere, it's kind of, you can think of it, I think, as being a result of the northerly flow that's set up by the mountains. But when you look at upper levels, it's actually more complicated than that. And in the upper troposphere here, all three terms are actually important. And in particular, over the Mediterranean, the vertical advection term is being balanced by the zonal advection term. So while you have descent over the whole depth of the troposphere, I think the balance that's involved is a bit different at the upper levels from the lower levels. And it seems like an interaction with the mid-latitude westerlies is important in the upper troposphere. So in the upper troposphere, the dominant balance in the thermodynamic budget between this term, so the climatological zonal wind, advecting the temperature anomalies induced by the mountains, and the vertical advection. And so it turns out the mountains induce this warm anomaly here, and then the mid-latitude westerlies interact with that. And I think this is kind of completely analogous to Rodwell and Hoskin's arguments about the sloping isotropes. So the mountains make it warm, they make the isotropes slope down more, and so as the westerlies come along, they're going to have more of a descending component because of what the mountains have done. Whereas in the descent in the lower troposphere is just really a direct response to the circulation set up by the mountains. Okay, so just finally, I've only talked about the summer so far. The mountains seem to have, the Zagros Mountains in particular, are having a pretty important contribution to the subsidence there during the summer. So what about in other seasons? Is their influence restricted to the summertime? So this is the summertime influence. And then this is what happens during the winter time. So during the winter, we're in this much more zonally symmetric downwelling in the subtropics because of, that's just kind of like the Hadley cell descent. The descent is also further south, so it's not really centered over the Mediterranean. And the Zagros Mountains really have very little influence on the large-scale circulation during the winter time. They kind of just have a local influence that's kind of noisy, where we've actually flattened the mountains. And this is true of the other fields too. They don't produce any upper tropospheric wave trains or any meridional wind anomalies either. So that they really don't seem to do much in the wintertime. And if we look at it, we can look at the seasonal cycle of subsidence. So this is averaging subsidence over this box here in the central to eastern Mediterranean. This is in the full topography world. So you've got subsidence for the whole year, but it really ramps up during the summertime when the Asian monsoon kicks in. And then this is what the mountain, the Zag Flat simulation looks like, so without the Zagros Mountains. And so what you see is that the descent is much weaker when we don't have the mountains during the summertime, as we've already seen, but the mountains really don't do anything at any other time of the year. And then just for completeness, I'll just show the Atlas Mountains simulation, really demonstrating that their influence is really pretty minor on the descent. The reason I wanted to show the seasonal cycle is if you compare this with the incident flow that's on the topography. So this is taking a box averaged over the Zagros Mountains and just looking at what's the incident flow that would be there when the mountains aren't there. And the mountains only really seem to have an influence when the incident flow is easterly. And they don't really seem to do anything at all to the large-scale circulation when the incident flow is westerly, which is kind of surprising because the other bigger mountain ranges in the world obviously have a big influence on the circulation when the flow is westerly. So I don't completely know what causes that asymmetry, but I think it's to do with the meridional temperature gradient and how the vorticity and the temperature want to behave. Because if you have easterly flow, if it wants to go up and over the mountains, then it's going to go north. And that's what the vorticity also wants you to do. Whereas if you have westerly flow coming along, it wants to go up and over the mountains, thermodynamics will make it want to go north, whereas the vorticity makes it want to go south. So I think that could be what's causing that asymmetry. And we're kind of working on some idealized experiments to demonstrate that. But we can see in the full GCM, it's really only when the easterlies are there that the mountains are doing much to the large-scale circulation. So then that raises the question of why do we have these incident easterlies during the summertime? And so perhaps the answer is obvious already, but it just demonstrates it that an obvious thing that's going on here is the Asian monsoon. So we wanted to see, well, can we reproduce these easterlies from scratch in a stationary wave model, and then we can pull apart what's responsible for them. So from scratch, I mean we can start off with the zonal mean basic state, put in the diabatic heating, put in the topography, the transient vorticity fluxes, and then see, can we end up with the 3D incident flow on the Zagros Mountains. So this is the flow we're trying to produce from the full GCM, and then this is what we get in a stationary wave model. So it's not perfect, certainly over the Atlantic, but we can reproduce these easterlies that hit the mountains in the stationary wave model. So then we can use the model to say which parts of the diabatic heating or topography are important. And so the obvious thing to do is check what the influence of the Asian monsoon heating is. So this is the full condensational heating that you have during the summertime. We've got all this heating over Asia. We have these easterlies hitting the mountains. Then when we take away this condensational heating here, it modifies the easterlies quite a bit that hit the mountains. It's kind of hard to tell just from looking at this, but if we look at the difference between these two, you can really see that this heating is giving rise to this lower level cyclonic circulation that produces this flow from the northeast that hits the mountains. It's actually not as simple as just that. You need to have that and Tibet. And if you don't have Tibet, then the easterlies are also not hitting the mountains. But really, it's during the summertime, we've got the Asian monsoon, as well as producing the descent over the Mediterranean, is producing the easterlies that are hitting the Zagros Mountains, that is then producing further descent in the region. So just to conclude on the climatological aspects, that both the Zagros and the Atlas Mountains seem to do the same thing. It's kind of fortuitous by how much they're separated, and that they're both conspiring to give you descent in the same region. But really, the Zagros Mountains are the most important. And they're giving about 30% of the descent in that area during the summertime. They only really seem to have an influence when the flow is from the east, as occurs during the summertime. And they seem to be responsible for about 20% of the Mediterranean moisture deficit, at least in the model. So I just have a couple of more slides that I just want to talk about, which is really the whole motivation for this work, which I have not yet got to dealing with, but we have some very preliminary results to do with it. So this may change, but I just wanted to show them anyway to demonstrate what the motivation was. So when you look in CMIP5, future minus past, you have these really localized circulation anomalies are produced in the future over the Mediterranean. You get this bullseye anticyclonic circulation. This is geopotential height in the future. And accompanying this, you can see this. Sorry, this is in the winter time. This is not true in the summertime. You have this localized descent here in the central to eastern Mediterranean during the winter time in the future. And so I was kind of motivated by Rodwell and Hoskins to see, well, what's the influence of the topography in producing this localized descent here during the winter time. And so the hypothesis was, well, in the future, the tropics are expanding, so maybe in winter time, you're more likely to have easterlies hitting the mountains, and then they would be producing this localized response during the winter. So the winter would become more like the summer in the future in terms of the flow that's hitting the mountains. And so again, these are very preliminary results, so don't take too much from them, but this is looking at CAM5 simulations, 4 times CO2 minus 1 times CO2 difference in vertical velocity. So the full topography world, CAM5, gives you this localized descent in that region over the central to eastern Mediterranean. And when you've removed those mountain ranges, the vertical velocity response becomes a bit more diffuse, and it's not as focused in this region. It seems to be about 2/3 of the magnitude of what it is with the mountains present. So actually, I think the mountains were not as important in the future as I was hoping. They're certainly not responsible for that big bullseye circulation change that you see, but I think they are having an influence in localizing the descent and probably making this region drier in the future than it would be without the topography. But that's something that needs to be looked at in more detail in the future. So I'll finish there, and thanks for having me.
Thank you. So, questions?
So the 20% deficit in the P minus E,
Yeah.
what do you think the prescribed SST contributes?
Yeah, I'm not sure. So SSTs they're not different between the simulations with and without the
Yeah,
mountains.
then you are enlarging the difference between the air temperature and the water temperature.
Right. So do you think the flow that's being set up by the mountains would have a big influence on the SSTs?
You might be overestimating
Yeah.
the evaporation.
Could be. I actually ran these experiments originally with slab ocean model with CAM3, but it turned out like CAM3 I think it wasn't a problem in the end because we got the same answer, but their climatological circulation in the Mediterranean wasn't very good, and so I was worried about using it for this. But so I can go back and look at those runs because they had slab ocean, so then it would be able to respond. We definitely got the same atmospheric circulation changes, but I didn't look at the precipitation and evaporation in those runs, so I could test that.
Yeah, actually, I just want to follow up on that because it's interesting because in summer you don't have much precipitation anyway, so you have a strong deficit. So, and your mountains sort of enhance the deficit, but what does it really mean for hydrology in that region? Because you are not getting precipitation anyway, so you are getting less if you remove the mountain, it's less evaporation from the ocean. So, but what impact would it have on
I guess it's less evaporation from the land too. Like it was bigger over the ocean, I guess, because there's more water to evaporate. But like over Italy as well, it was still about 20%. So I guess you could imagine that. I'm not expert on hydrology, but evaporation from the land surface would be less if the mountains were not there 20% rise.
So I have a.
Yeah. Okay.
Sorry. Yes, this last part remind me of that nice paper when I was at graduate, when the group had a very nice interaction with Hoskins group. Well, anyway, when I look at the map of the near the central Africa during summertime, it migrates. I mean, the rain bands usually migrates more northward. This is one thing. Second thing that from your substance maps, usually overall the substance is much stronger than the setting motion. Or if we do local average is only average, locally we'll get more or stronger substance. So these two things reminds me probably more or less related to the local meridional circulations, for example, local Halley circulation. We may say that. So what do you think about that point?
Yes. Yeah, so I have seen some papers that have argued against the Rodwell and Hoskins saying that it's more of a meridional, kind of a, I guess more like a Walker type circulation that's giving the descent. Is that what you mean? Or?
Well, two sense actually seems to point to the local meridional circulation as a local Hubble circulation rather than in that direction.
But I guess that they can, so I haven't redone the Rodwell and Hoskins experiments because it was much more difficult to produce the climatology in the stationary wave model than just producing the response to the mountains.
Right.
But I mean, their argument is they can reproduce that descent there by only putting in the heating over Asia, which suggests that it's not heating over Africa that's producing a local Halley circulation. But whether maybe that wouldn't hold true in other models, I don't know.
Right.
So first, I want a clarification in terms of terminology, because in the Rodwell and Hoskins paper, they spoke of diabatic heating in the South Asian monsoon. So you spoke of Asian monsoon. So in your simulations, are you including simulations in diabatic heating in East Asia also?
Oh, so actually, you mean these stationary wave ones? This where we took out this heating.
Yeah.
So here we took out heating in the whole box. And I think it's not to produce the easterly winds that hit the mountains. I think you have to remove all of it. I think I think the heating everywhere is important there for getting the total easterlies. In the full GCM experiments, we have all the Asian monsoon heating everywhere.
So that would be an important departure from the Hoskins picture, Rodwell Hoskins picture, because they placed their diabatic heating source over India or South Asia.
Sorry, I think I maybe rushed over that a little bit. I think for the part where they showed the topography influence, they had put in the full heating, I think, of the real world rather than the idealized heating. But I don't know so they talk about the flow being from the west, but then in Rodwell and Hoskins 2001 paper, they showed that the flow, they put in the Asian monsoon heating and they get the easterlies hitting the Zagros Mountains. So whether the flow in their model was actually from the west or not, I don't know. But that could be, I think definitely there could be reasons like that for the difference, because we can see that both the Atlas Mountains and the Zagros Mountains do the same thing. So if you have different incident flows, then it could be that in a certain case the Atlas Mountains could become more important than the Zagros Mountains. So maybe that could account for the difference.
Okay, thank you.
Yeah.
Right.
So you were emphasizing the descent along the sloping isotropes into the central eastern Mediterranean, and I assume, that's somewhat of a thermodynamic, isotropic, diagnostic type of vertical motion, along.
Yeah.
So I assume in that same region, there's a quasi-geostrophic, signal given that stationary wave train. So the descent is the result of the stationary wave train, the fact that you would expect it in that region. Just thinking of things like quasi-geostrophically, not just along thermodynamic isotropes. So if you calculated some QG diagnostics, you would see descent
So
as
you
you would
mean like
expect.
take the upper level convergence
or any Q vectors or any kind of diagnostic that would show, given that wave train, which I guess would make sense because your isotropes are sloping down, so you're between kind of the ridge and the trough region. at mid-upper levels. So you would expect, I think, large-scale subsidence there as a result of quasi-geostrophic thinking.
Yeah, maybe
and then, or also just thinking of PV advection, going from low to upper level low PV to high PV, and along that. So I would just wondering
maybe that would be a cleaner way to discuss it.
Yeah, and then the other question I had, the quick one, was is that obviously there's a large scale signal and response. Is there any diurnal variability with? I guess your flow over the mountain, and what I was intrigued about, and the vortex stretching and so forth, assumes there's some stability, but in the daytime it's a very deep, well-mixed layer. So there's not a lot of potential for adiabatic warming and compression during the day. So I'm wondering, is it the nighttime you're getting most of the thermodynamic response because you have a nocturnal inversion or some sort of stable layer, or so this structure above the mountain I'm wondering about, because typically in the summertime you're dealing with an adiabatic layer over the mountain, and so there really isn't any potential for warming and cooling at those times.
During the daytime.
Yeah.
I don't know, that would be interesting to check. Unfortunately, I only saved the daily means. This is too much data to save the 6 hourlies. But I mean, you could run short ones. I mean, this becomes, it's very robust after even just 10 years. You can kind of see what's going on. So I guess I could run it again and I'd pay higher frequency.
I'm guessing there's pulsing going on diurnally off these mountains, depending on the time of day, and you're looking at the aggregated effect of that somehow.
Yeah, that would be really interesting to look at.
Especially with easterlies, you actually get a lot of transients. Actually, you can't support stationary wave easterlies. You're getting a lot of transients that when the wind set and stability set up. So that's an interesting question. Okay, John?
Yeah, I'm a little confused why during strong westerlies you don't get any subsidence at all from the mountains. I understand when you're talking about thermodynamic balance, but orographically.
Well, there is a little bit, and I think it's kind of noisy, but we can go back to it. And I think it's kind of in the way you would expect if you, from the thermodynamic argument. So there's ascent generally, I mean it's noisy, I think because the signal is small, but there's ascent to the west and descent more to the east, which is what you'd expect just from the flow going up and over it. And accompanying that, there are weak southerlies and weak northerlies. But yeah, I was also surprised at how little influence the mountains have when there are westerlies. And have done some idealized experiments. I'm not sure if they're very good because they were not in a balanced state. It's kind of hard to have balanced states doing what I wanted it to do. But basically, we put in barotropic easterlies or westerlies hitting the mountains, but you also put in a meridional temperature gradient, so it's completely not in thermal wind balance. But you can reproduce this asymmetry that if you have barotropic westerlies and south to north temperature gradient, you just kind of get this weak ascent to the west and descent to the east. Whereas if you do the same but for easterlies, then you get much bigger circulations and much bigger influence on the larger scale circulation. But it's confusing because obviously the Rockies and other mountain ranges, like the Andes, obviously do something in westerly flow. So I think it's worthwhile doing some idealized experiments where looking at the dependence on the meridional, the width of the mountain range, or how those kind of things affect it, because clearly this having no influence on westerlies but a lot of influence under easterlies does not hold for all the mountain ranges in the world. So there's got to be some reason why that would happen.
And it's surprising that you don't get sort of a Rossby wave response downstream for the westerly.
Yeah.
For easterly, you understand that because you can't have easterly waves in easterly stationary wave, or stationary wave in the easterly is downstream because it doesn't. Well, it just doesn't support the stationary wave.
The easterly flow.
Yeah, for the easterly flow. But for the westerlies, you would expect stationary westerly.
I think it probably is there. It's just so small. Maybe I have it in the meridian.
but that's winter though. So
Yeah.
you show the summer, the upper level in summer.
Oh,
you
yeah.
get this
So here.
must be wave. So I would expect that for winter, apart from the local response you see in the low level, you should probably have downstream.
Yeah, no, it doesn't really do much.
All of the Himalayas are really starting to
probably
dominate
Himalayas
westerly. You almost see it here. I mean, it's
Yes.
swallowing up the whole Zagros influence.
This is in the wintertime, the Zagros influence of lower or upper tropospheric meridional wind, so it's really not doing anything. And lower tropospheric meridional wind, it's doing a bit which is consistent with the thermodynamic arguments that if you're going up over the mountains, you have to be going from toward the north. And then there's descent and northerlies to the east of the mountains. But it seems like it's too weak to really do anything about. This is in the full GCM.
You compare the CIMIC 5 model, the Futuron and the Pastron, the differences between them and the boreal winter.
Yeah.
They have, and you assume that that is similar with the summertime. So is the deviation between the future and past, the temperature is the same with it? So how?
Yeah, sorry, I should have, that was very preliminary, so I don't know if what my hypothesis was, it's really the answer, but I think what I was hoping was that during the winter time, there's more scope for the winds that are hitting the mountains to be changing sign, because in the winter time, you're kind of on the border between easterlies at low latitudes and westerlies at high latitudes, whereas during the summer, you've already got easterlies hitting the mountains. And so the thinking is maybe as that border shifts forward, during the winter time, you have more of an influence of the mountains in the future because they have easterlies. But whether that's the case or not, I don't know. So you should probably just forget about that for now. But I just wanted to demonstrate what the main motivation for looking at it was in the first place, to try and understand that.
I'm curious about how the Mediterranean ocean surface influence on the subsidence of the atmosphere. Because what if it is a land surface but not an ocean surface?
I don't know. I think it wouldn't affect the large-scale circulation, but then the evaporation would be different because
Yes, because they have different heat capabilities. So maybe in summer it's a cool shock and not a heat shock.
I think it would. I feel like the circulation anomalies will be the same because we can reproduce them in the stationary wave model that doesn't have any of that stuff. We can really get the same structure. What might be different would be the hydrological impacts. So it wouldn't be evaporating from, well, it would probably be really dry, so there wouldn't be any water to evaporate.
Well, it may also, but it may actually have some impact on the flow though, because actually you get much warmer, probably.
So you mean
the land surface would probably be warmer than the Mediterranean Sea, so it could actually change the flow a bit.
Like the
basic
incident, the basic state incident flow.
Well, very interesting discussion. I think we probably should continue it at lunch. So, yeah, let's end it.